Hello and welcome to the course on manufacturing technology theory and practice. Now, I would like to describe how a bevel and a spar gear can be fabricated in the lab. So, I will show you some slides so that you could understand in a better way when you will go to the lab, just before going to the lab. So, this will be the introduction to the fabrication of the bevel and the spar gears, and then in the laboratory we will show you how these gears are actually fabricated. So, if you see here, this is making a spar or a bevel gear. This section first describes the procedure to make a bevel gear, followed by the description of making a spar gear. So, you can see the three dimensional or the pictorial view of a bevel gear. So, this bevel gear has to be fabricated in the machine, okay, in the milling machine and the turning machine together. So, let us see the steps. First of all, we have to have the nomenclature of the bevel gear in the drawing. So, if you see here in this drawing, this is the two dimensional, this is the actual drawing of this. So, this is hatched, okay, this is metallic, this is the these are the teeth of the bevel gear. So, in here this is the center line, and with respect to the center line, this is the radius. So, this point is the point along the pitch circle, this is called the pitch cone. Okay. This is the cone, all right, and here is the like in case of the pitch circle diameter you see in the spar gear, for example. So, here this from here to the radius, this is the center line. So, this from here to this point, all right, from one teeth to another teeth and from one tooth to another tooth, and this is the pitch circle line. So, this is called, in case of bevel gear, this is called the pitch cone, all right. And the other two lines, one is called the face cone here, okay, this one, and another is called the root cone. So, this is the root cone, this is the face cone, and for this tooth similarly this is the face cone and this is the root cone, all right, like in case of here. This therefore, from this point, okay, to this point, this is the outside diameter, and the pitch diameter will be from this point to this point, okay, pitch diameter, and this is the half of it. So, this is the radius, half of this pitch diameter. This is the outside pitch, this is called somehow, in case of bevel gear, it is called the outside pitch diameter. Now, from this line, that is the pitch circle of one tooth, up to this distance is called the back cone radius. Now, here you can see the two angles. One angle is the angle between this line, that is for the, as I said, there is the face cone, and between the pitch circle here. So, this angle is called the addendum angle, all right, and between the pitch circle and this line, which is the root cone, this angle is called the dedendum angle. So, addendum and dedendum principle you might be knowing from the from your BTech first second year level, all right. Now, from this point where these lines, because these are cone, okay, these lines meet, from this point to this point, to the extreme end point of the bevel gear, this is called the cone distance, which is L. Apex cone, apex of the cone, pitch of the cone is here, all right, and similar to the addendum and the dedendum angle, we have the addendum, and this is called the dedendum. The angle is addendum angle, this angle is dedendum angle, this height is called the addendum, this height is called the dedendum. Okay. Now, inside pitch diameter is here, and this is the once again outside pitch diameter. From here to here is the outside pitch diameter, from here to here it is the inside pitch diameter. Now, there are two more angles. One is the face angle between the axis and the line which we called as the face cone, all right. This line you see, and this axis, this is the face angle, and this is the pitch cone angle, this is the root angle. Pitch cone angle is between the pitch line or the pitch center and the center line. Now, the root angle is between the root cone and the axis of the bevel gear. This is the root angle here. So, we have the root angle, we have the face angle and the pitch cone angle, all right. So, this is okay. Another thing is there is a face width. These are all the parameters or the nomenclature of a bevel gear that we should be knowing, because according to these nomenclatures we will have the parameters calculated or given. Some of the parameters have to be calculated and some of the parameters will be given. The calculations of a standard straight bevel gear, these are the following. Now, you can see that this is the shaft angle. Shaft angle is the angle at which the two shafts, input and the output shaft, two shafts are located. So, in case of bevel gear, for example, the another shaft which will be in touch with this, okay, or in coupled with this gear, this shaft has to be at an angle of 90 degree with the axis of this gear. Okay. So, these are the two shafts. On this shaft there is a bevel gear, on this shaft there is a bevel gear, and those bevel gears are meeting for transmitting the power from one shaft to the another shaft. So, the bevel gears normally they are used, as you know, that for transmitting the power from one shaft to another shaft which is at a 90 degree angle, whereas as a spar gear, you have seen that earlier, that spar gears are used to transmit the power between the parallel shafts, and the bevel gear is between the perpendicular shafts. So, therefore, the shaft angle will be 90 degree. Module will be given by us. What is that module that we need? Depending on that, we will give this value m. Pressure angle also will be giving, which is alpha. Number of teeth, it is our choice, Z1 and Z2, depending on what is the transmission ratio you would like to have. You can have the number of teeth, because as I said that the transmission ratio is the number of teeth in the input gear and the output gear. So, this is Z1 and the Z2. Okay. Pitch diameter we have shown to you, this is that, and this pitch diameter is equal to Z into m, meaning that what is the number of teeth that we have selected into the module that we have decided. These two products, this is a product of these two parameters Z and m, it will give you the pitch diameter. Now, the pitch cone angle, this is given by tan inverse of sine of the shaft angle divided by this ratio of the number of teeth of the input and the output shaft plus the cos of the shaft angle. So, this is a formula that can actually be derived from the geometry of the bevel gear. I am not going to derive it right now. So, this is derived and this is given in any kind of a handbook that you can see, and this is how you can find out what is the pitch cone angle. See, these parameters have to be calculated, because according to the pitch cone angle you have to fit in, you have to put your shaft, otherwise the bevel gear will not be produced correctly. Cone distance, well, pitch cone angle for one it is this, and for the mating one it will be of course shaft angle minus this, because this is the concept of the pitch cone angle. Cone distance is Re, this is d2 divided by 2 of the sine of the delta 2. Delta 2 is here, all right, for the another gear, and d2 is for the pitch diameter of the output shaft. So, d1 is the input shaft and d2 is the output shaft. Now, the cone distance Re, this is given by this formula, d2 divided by 2 sine of delta 2. Face width is Re divided by 3, or normally it is taken as the 10 of the module. RE is the cone distance. Either 1/3 of this cone distance is the face width, or it is the 10 times the module. This normally the face width is given here. So, why it is 10 times of module? This is taken from the design point of view and the manufacturing point of view, in the sense that how these gears are working. Okay. If the module is such, then width has to be at least 10 times the module. That is what the concept is. This is what experimentally or in practice, when the bevel gears work, this is from the practical experience, we can say in one word. Addendum is module and the dedendum is 1.25 module. Okay. So, this is important thing, that this is the module. Now, depending on how this bevel gear will be working, in which conditions it will be working, how much torque it will be transmitted, it will transmit, depending on that we actually select the module, because if it is a very high kind of a torque that is to be transmitted, then the module has to be bigger, because the teeth have to be fatter. So, this is how the addendum or the module is decided, and this is calculated by the module. And when you are finding out the dedendum, this is the dedendum here HF, this is normally 1.25 times the module, or 1.25 times the module that you have selected. Now, the dedendum angle, this is given by tan inverse of HF divided by RE. HF is the dedendum and RE is the given here cone distance. Okay. So, RE can be found out from the diameter of the pitch diameter of the second gear, output gear, and the pitch cone angle of the second gear, 2 sine of that angle. Alright, pitch cone angle is given here, that is this for one gear, and the shaft angle minus this pitch cone angle will be the pitch cone angle of the second gear. Now, the dedendum angle and the addendum angle we can find out by this way. So, dedendum angle is when you are dividing this by the dedendum, and obviously for the addendum angle you are dividing that by dividing the addendum by the RE. RE in both cases have to be the same. This RE is given in the calculated already as a cone distance. Outer cone angle is delta plus theta A, delta minus theta F will be this, that is the root cone angle. Okay. So, these are already theta F, addendum angle, dedendum angle, these are already calculated, delta is calculated, pitch cone angle. So, you can find out what is the outer cone angle, what is the root cone angle. Therefore, outside diameter you can find out, because the delta is known, HA is known, D is known. Alright. So, D means D1 and D2. Okay. So, these are the two diameters. Now, pitch apex to crown, this is X, you can find out from the drawing. This is here cone distance, and the pitch apex is the apex of the here, apex is here of the cone. So, this is given by simple using the geometry, simple geometry, and width you can find out. Inner outside diameter will be this, again by this formula you can simply find out. Now, let us see how this knowing or calculating, knowing some of the parameters and calculating the remaining parameters like I have shown it to you, we can actually now find out how this can be manufactured. So, this is the production drawing of a typical bevel gear. You can see the production drawing here. So, the drawing that you are familiar with, that all the parameters have to be there, this is the side view and this is the pictorial view of that. Okay. So, here this is the engineering drawing with all the dimensions, this is the title block and all those things. So, this is the final drawing that has been made with all the parameters. Okay. Now, how to make that bevel gear? First step is identify the raw material. Okay. So, the raw material out of which you are actually going to make the bevel gear, it may be a mild steel cylindrical piece, it may be a steel piece, or the material that you desire. Okay. Now, the step 2 is mount the cylindrical workpiece in the chuck. So, since it is a cylindrical workpiece, normally we mount it on the self-centered chuck, where the center of that workpiece will be coaxial with the center of the spindle. Okay. So, therefore, it is a 3-jaw chuck. You can see that 3-jaw chuck, it is mounted on the 3-jaw chuck, and it is self centering. That is why if you rotate from here, if you rotate one of the jaws, all the other 3 jaws will be, all the other 2 jaws will be rotated. This will show you in the lab. You can see this. Measure the diameter and turn it to the size. Okay. Now, the size is given to you. This is the external diameter. Okay. This is the internal diameter. Okay. All these sizes, all these dimensions will be given to you. So, accordingly you measure and then turn it to the size, so that accordingly the diameter can be turned. Step 4 is drill a through hole, because we have a through hole here, as you can see this, okay, through hole here to hold this inside, this one, or this is given in the dotted line, shown in the dotted line. So, drill a through hole. Again, the drilling hole, as you can see, that this can also be done in the turning lathe. So, for that you have the headstock here, where you are mounting the workpiece through a 3-jaw chuck, all right. And in the tailstock, on the opposite side of the machine tool, you have the tailstock where you can actually mount the drill that you will see in the lab, and that drill will not be rotated like in the drilling machine. That will be rigidly fixed in the tailstock, and the tailstock can be moved towards the rotating job which is in the headstock of the machine, okay, and the through hole can be made. Then step 5 is move to the milling machine, because this completes the operation in the turning. That means you are making the job with the, here you can see that in the job you will have a part, I mean you will have a section where it will have the conical part. So, this is for cutting the teeth, bevel gear teeth, and this also has been made in the turning lathe. After this, the milling process will start. Milling process will start on that blank which has already been made in the turning lathe to cut the bevel gear teeth. Mount the gear blank in the indexing head. This is the indexing head, part of the indexing head. This is the 3-jaw chuck, and the entire 3-jaw chuck is mounted on the indexing head. You can see this indexing head here. Now, the indexing head is used for indexing the subsequent teeth. That means, after cutting one tooth, how you are going to rotate the blank, so that the blank could be ready for cutting the next tooth. So, in that case we have to know all those calculations, all those angles, okay, and number of teeth that you are cutting. So, you can see the blank, this is mounted in the indexing head. Now, this is the indexing head. Adjust the angle of the indexing head, because this will be the same as the angle that has been calculated here, okay, this angle. So, without that you cannot cut the bevel gear. So, you are adjusting the head angle, mount the cutter on the arbor of the shaft. So, this is the horizontal milling machine that is used for cutting the bevel gear, and here is the cutter. So, how to select the cutter is a standard one. So, you will see in the lab that there is a rack. On the rack there are different kind of milling cutters, and each of the milling cutter, in each of the milling cutter there is a leveling, that particular milling cutter can be used for cutting these many to these many teeth, let us say from 30 to 60 teeth, okay. From 60 to 80 there is another gear, for example I am telling you. So, you will see that in the rack there are many different kind of gears, and each of these gears is identified to make the particular number of teeth, and that depends on the profile. So, depending on that number of teeth you have a profile, and that profile will be conformed to that particular milling cutter, and you have to select that particular milling cutter for cutting those many teeth or the particular number of teeth. So, this milling cutter will have a central hole, and at the center also along with the hole it will have a keyhole. So, using that keyhole and the center hole, so this milling cutter is mounted on the arbor of the horizontal milling cutter, horizontal milling machine, and this attachment will be shown here in the lab, and you will be shown how this milling cutter can be mounted on the arbor. So, this you can see in the close view that this is the cutter which is mounted on the arbor, and this is the workpiece that has been made in the lathe machine, all right. And here in this inclined surface, which is according to the angle which is set here, this angle is according to the calculation that we have done, I have shown it to you, and then the one by one tooth after another tooth the gear is cut, and finally what you get is this. Okay. So, these steps in details can be seen here, all right. Select a lathe machine. So, here are the details of the lathe machine. Here we have the tool, here we have the tool post for example, where the tool is there, all right. Tailstock is here as I showed it to you. Here is the headstock, inside that we have the gearbox. This is the chuck, in this case it is 3-jaw chuck, all right. The gear lever are here, here is one, here is another. So, with this we can change the number of RPM of the rotation of the spindle. Okay. That means, inside this headstock there is a gear train, and you will see the gear train. We will open the box for you, and then depending on the number of teeth of the input and the output gears and intermediate gears, you will get the different kind of RPM. So, those different RPMs can be obtained by moving these spindles one or the another one. The saddle is here, this is the saddle which will move along with the tool post, okay, along the bed of the machine tool, that is the lathe here. So, this is the lathe bed, okay, and this is the lead screw. Here you can see the lead screw, all right, and this is the cross slide. Cross slide means that if you rotate this handle, the slide will be moving perpendicular to the axis of the spindle or axis of the workpiece. Okay. Tailstock, I have already told you that in the tailstock you can have the drill mounted or the centers mounted for supporting the long cylindrical jobs on the center holes, all right. Here we have the coolant supply. So, depending on the type of the operation that is being performed, you need to have the coolant supplied, and coolant will be supplied in the to the machining zone between the tool and the workpiece, because the lot of temperature is produced, lot of the friction between the chip and the rake face of the tool or the workpiece, already machined workpiece and the flank face and so on. So, those surfaces of the tool particularly have to be cooled down. Why I say for the tool particularly? Because tool surface have to be protected, otherwise the tool geometry will be lost, all right. Of course, when you are putting the fluid, it will come to the workpiece as well in the machining zone. So, the workpiece also will be cooled down, because otherwise the workpiece becomes very hot as well. So, there could be some kind of a thermal deformation of the workpiece. So, for all those purposes the certain type of coolant is supplied, so that the tool as well as the workpiece remain cool. Now, after that it will be cylindrical job will be mounted on the 3-jaw chuck. Here the 3-jaw chuck in the close view we can see this is the workpiece, all right. The value will be added to the workpiece, meaning that you will have to have the surface made, proper surface made, then the conical head has to be made, so that the gear can be cut, because right now it is the turning lathe, it is the lathe machine on which the work is going on, but ultimately we have to cut the bevel gear, and the bevel gear will be cut on the milling machine. So, here we will see that this is the self centering chuck, as I said that this is the 3-jaw chuck, these are the jaws, this is one jaw, second one, and this is the third one, and this is the cylindrical workpiece which is mounted. You can rotate this, so that all the 3 jaws will be simultaneously moved coaxially, and the part will be mounted on this, so that the axis of this cylindrical workpiece will be coaxial okay, with the axis of the spindle of the machine. This is important because otherwise what will happen, that if you are machining without having the two axes coaxial, then the machining will not be appropriate. It will be either tapered or out of roundness, or depending on the the amount of coaxiality or non-axiality. So, measure the diameter and turn it to the size, okay, with a vernier caliper, because it will actually give you the more precision of the measurement. So, here what is the what are the processes that is being done, here it is given here. Turn the cylinder down to the size. Okay. So, this diameter, outer diameter of the body of the shank, this is being turned here, as you can see that, and this is held in the head that has already been machined. This head will be cylindrical head so far, without having the tapered turning, because tapered turning will be done here. All right. So, therefore, it is cylindrical part as such, and this is held here in the 3-jaw chuck, and this other part will be turned. That means, this part length will be turned. Third step is machine the conical surface by tapered turning. So, this surface where the teeth will be cut, this surface has to be produced, this is the surface, and the whole gear blank is made here, as you can see that. This is the tapered turn, this is the cylindrical surface, this is the cylindrical surface. All right. Now, the next step is first perform the center drilling. Okay. Center drilling is required to make the centers on both sides, so that the drill can be penetrated properly. Okay. So, before drilling the hole, the center drills have to be used to make the center drills, perform the center drilling. Then drill a pilot hole with a bigger drill. Okay. So, some diameter of the pilot drill has to be selected, so that initial hole can be drilled. Then you take a larger diameter of the drill and enlarge the pilot hole. So, pilot bore or the pilot hole has been made with a diameter of the drill less than which is required for the internal hole, I mean to say this hole, this diameter. Okay. So, here you will take a diameter of the same size, so that the final hole can be made. So, here the diameter is less than the diameter here, then the final diameter is selected, final diameter of the drill is selected, and the hole is drilled. Gear blank is ready to be loaded in the milling machine. So, now we will go to the milling machine. Here is the milling machine, where that part will be loaded and then the gear will be cut. So, this is called the overarm. Here on this the spindle is located, is hanging here as it is, and this is the arbor on which the milling cutter will be mounted. This is the arbor support, if you can see here. Okay, this is supporting the arbor, and this is the entire column is shown here. This is the column, this is the cutter. Okay. Indexing head, as I showed it to you, and on the indexing head you have the 3-jaw chuck on which the part will be mounted. This is the arbor, as I said, this is the arbor shaft. This is the lathe, the milling machine bed. This is the bed. All right. And here we have the cross slide handle. That means, if you rotate this, the cross slide will be moving. So, it will be moved along this side. So, if you see that here there is a dovetail, and on this slide way the slide will be moving perpendicular in this distance, axial distance, and this is the base on which the entire milling machine is located. Vertical travel is here. So, with this you can have the movement in this direction, okay, and with this rotation of this handle, the table will be moving in the direction perpendicular to the vertical direction. Okay. Now, the gear blank is mounted on the indexing head. This is the indexing head, as I said, and this is the chuck. This is the 3-jaw chuck. Okay. Now, the indexing head, gear blank mounted on the chuck, how you decide what is that, why indexing head is required. As I said that this is required to rotate the blank from the position of the one tooth to the another one. All right. Now, this is very simple how it actually can be done. The formula is 40 divided by n. Okay. This is the formula. Okay. Why it is 40 by n? 40 because inside this indexing head we have a worm and worm wheel. Okay. And I have shown it to you that worm and worm wheel has a transmission ratio of 1:40. So, that is what we have used, and n is the number of teeth that we have to actually cut. Okay. So, here we have the inside is a worm and worm wheel. Worm we are rotating. So, worm wheel will rotate the spindle along with the workpiece. Suppose we have 20 teeth. Okay. So, it will be 40 by 20, which is 2, that is 2 rounds. If we rotate the index plate, 2 complete round will give you the actual pitch for cutting the 20 teeth. Suppose you have to cut 18 teeth. Okay. So, it will be 14 by 18. So, this will be 4 by 18, right. So, now you can see that this is 2 complete rotation and then 4 rotations out of 18 holes. That is how we actually make it. For cutting 18 teeth, formula is 40 by n. So, 40 by 18, which is 2 complete rotation 36. So, 4 by 18, meaning that if we have an indexing plate where the peripheral number of the holes are 18. So, after moving 2 complete rotation, you move 4 of the smaller holes 1, 2, 3, 4, where it will be 18 holes total in the periphery. That is how the calculation is made. It is simple, and you quickly make a calculation, that is 40 by n, how many times the indexing plate has to be rotated and how many fraction of rotation has to be given. So, that will be the indexing for the teeth for moving from one position to another position of the teeth. So, this is the gear blank mounted on the chuck. All right. Here adjust the angle of the indexing head, as we said that this angle has to be adjusted with respect to the horizontal, and you can see a graduated plate here. That graduated plate will tell you that what is that angle, and that angle we have already calculated. Okay. According to this angle, the indexing head angle, indexing head has to be adjusted with respect to the horizontal. So, let us say it is about 40 degree. Okay. We have calculated, I think it was 39 point something. So, about 40 degree, and then the next steps are this is the arbor shaft. So, from the arbor shaft you have to remove the support and you have to remove all the spacers and all, so that the cutter can be mounted. Now, the cutter goes in here, and the cutter, as I said, is mounted on the arbor with the help of the key and the keyhole. Okay. So, the keyhole is there in the cutter and the keyhole is similarly there in the shaft also, arbor also. So, insert the cutter on the arbor shaft with the help of the key and the keyhole. Then you put the spacers, because the spacers are required to hold the milling cutter on the arbor properly. So, these are the spacers, and here we have the bearing bush. Okay. Now, bearing bushes and the spacers have to be taken back on the arbor. All right. And then the arbor support has to be placed on this bearing bush. This is mounting the arbor support back. Therefore, on this arbor the milling cutter is mounted, because to make the milling cutter we cannot always have the milling cutter left here. First thing. Second thing is we have to change the cutter depending on the requirement of the diameter, requirement of the number of teeth in the cutter. So, we have to change the cutter frequently. Therefore, normally after milling operation the cutter is removed. So, to remove the cutter you have to remove the spacers, you have to remove the support, okay, and then you are putting another gear, another cutter, and those spacers and the supports have to be mounted back. Then index and cut all teeth similarly. So, one tooth after another it can be cut. Okay. So, now you can see that one complete tooth has been cut here. Okay. After that you stop that rotation, move the indexing head according to the angle, according to the number of movement that I have shown you 40 by n, that you will completely see understand when you go to the laboratory, that how it can be rotated and how much it can be rotated, when we will show you in the laboratory. So, all the other teeth you cut similarly after indexing using the indexing head. So, once again you have to rotate that indexing head complete circle depending on the number of teeth that you are cutting. Suppose you are cutting more than 40 teeth. Okay. So, nothing, I mean the same formula can be used, 40 by let us say 60. Okay. So, it will be 4 by 6, 4 by 6 means 12 by 18, all right. So, that means when there is a on the periphery, if there are 18 holes, out of that only 12 holes you rotate, not complete rotation, but up to 12 holes. Okay. So, that is how you can cut any number of teeth that is required. So, here you have the bevel gear that you have actually cut it. Now, while doing so, you must have used this kind of tools, that is this the cylindrical blank, this is the drill with a 12.5 millimeter, this is the drill with 8 millimeter. So, if you remember that we had a pilot hole and then we had a final hole. So, these are the pilot drills that are used for making the final drilling, center drill for making the that is to marking, and this is required for the actual drill, the pilot drill and the actual drill to go properly. All the time you need a vernier scale to measure the diameter actually. This is the gear cutter that has been used. This is the single point cutting tool that has been used for making the turning and the conical shape of the blank in the turning lathe. Okay, spanners required to tighten, loosen the screw, and this is the drill chuck in which these drills are mounted. You can see these drills are of lesser diameter up to 12.5 millimeter. So, these drills are supposedly not transmit, but not required so much of torque for drilling the hole. So, therefore, the torque carrying capacity, as I told you earlier, of these kind of drills with a lesser diameter, it is less, and therefore, the shank is made as cylinder. So, for cylinders, for cylindrical shank, here is a drill chuck where we have the drill chuck is a collet type. Okay, collet type drill chucks you can see in the lab when we will show you in the lab, but thing is that collet type chucks, I will give you an example of a mechanical pencil. You have seen that mechanical pencil it has a collet chuck. So, this is equivalent or similar to the collet chuck where you can actually mount the drill with the cylindrical shank, and then the collet chuck has to have the taper Morse taper surface of its shank, so that the taper shank can go into the drill holder or the drill chuck. Now, these are the steps of a bevel gear. Once again, these are repeated. I am not going to show you once all of them one by one again, because this is the repetition. Now, for the bevel spar gear, okay, here is the pictorial view of a spar gear. This is the drawing, like we have made the drawing of a bevel gear. Here the complete drawing, engineering drawing of the spar gear has to be made with all the dimensions, and these are the parameters. In the parameter you have to write the number of teeth in the drawing itself. This is the module that we have given, cutter diameter, okay, depth of cut, internal diameter, tap hole, okay, and the indexing, how many rotations you have to make. So, that indexing will be made depending on the number of teeth. So, here probably the 20 number of teeth has been selected, so that the 2 rotations are made for the indexing. Raw material, you have to write what is the raw material. Here it is written mild steel, diameter of this is the blank diameter, all right. So, before you cut this, you need to have the blank, and the blank diameter is given here, okay, in the drawing. So, the steps are the following. Okay. So, identify the raw material like we have shown the steps in the bevel gear. Here mount the cylinder in the lathe, measure the diameter and turn it to size, drill a through hole like it is all like in the bevel gear, cutting the bevel gear. Assemble the gear blank in a mandrel, mount the mandrel in the machine, turn the gear blank down to size, okay. Move to the milling machine, mount the mandrel and the cutter. These are the same steps. I will show you in details one by one. Mount the driving dog for the indexing. This is something new for the for making the cylindrical part. Cut the gear teeth one at a time, all right. The procedure is well almost same as in case of the bevel gear, only thing is that here it is the straight teeth that you are talking about, and what you get is finally the gear, spar gear ready for the use. These are the steps. The raw material has been identified. This is a cylindrical job, in this case cylinder. Then the machine, this is the lathe machine on which this will be mounted. I am not going into details because I have already described how this can be mounted on the lathe and what are the description of the lathe. The same lathe can be used for making that, because what we are doing is we are actually turning, okay, turning the outer surface facing, so that the blank can be made for cutting the gear. You can see here this is mounted on the 3-jaw chuck, this is the cylinder, this is a blank, all right. Here this is the cutting tool that you can see. This cutting tool is on the tool post with the tool holder. Measure the diameter with the vernier caliper and then turn it according to the diameter which is required. So, while doing so, you have to finally see, measure with the help of the vernier again, that whether the proper turning has been done. Drill a through hole. Okay. So, first you have to have a center drill to mark the center, then you are using the pilot hole, then you are using the bigger drill for the for enlarging the pilot bore. This procedure as a matter of fact is the exactly same as the procedure I have already discussed in the case of the bevel gear cutting. Okay. Assemble the stepped gear blank in a mandrel. This is how the gear blank can be mounted with the spacer. This is the mandrel that will be supported between the centers. See, the gear blank is very small in the length. Okay. So, that length cannot be supported fully on the centers between the centers, it is not convenient. So, therefore, it is mounted on the mandrel, and the entire mandrel will be then mounted on the centers between the headstock and the tailstock. Okay. Here you can see that this is the mandrel, this is to be turned, this is the gear to be turned, and here is the dead center which does not rotate on the tailstock, and here there is this mandrel is held in the 3-jaw chuck. But now, since this is centers, okay, it can be mounted on the centers, and in that case there is this is the lathe drive dog. Okay. Here what happens is that you can have a center here, and that is on the center, mandrel can be on the center. Then with the help of the lathe drive dog, this is secured in the one of the jaws of the 3-jaw chuck. Okay. Then as the 3-jaw as the spindle rotates, this will transmit the rotation to the mandrel and subsequently to the workpiece which has to be turned, all right, and the where the cutter, I mean the teeth has to be made. This is the cutting tool which will actually turn this job, this surface. Okay. This is now turned to size, that means this is according to the diameter that is given, and this face is according to the length that is given in the drawing. Now, we move to the milling machine where the gear will be cut, teeth will be cut. So, you can see that the process will be more or less the same. Mount the mandrel in the milling machine between centers, mount the form cutter of cutting gear teeth. Okay. Here the gear that the milling cutter that will be used will be a form cutter. Okay. Driving dog for indexing made mounted here. This is the gear blank, okay, and this is the milling cutter mounted on the arbor, like we have shown you in the case of the bevel gear cutting. Indexing mechanism, each gear tooth is cut individually and then the blank is indexed to cut the next tooth. This I have already explained to you, that here in the drawing, if you remember, it was given that there should be 2 complete rotation of the indexing head or the plate. Okay. That means, we must be using the 20 number of teeth. If we have to cut 20 number of teeth, then 40 by 20 is 2, which is the 2 rotation of the complete rotation of the indexing plate. Okay. This is how one tooth has been cut. This is the milling cutter, form milling cutter, as I said. This is the workpiece, and here you can see the tooth is cut. Similarly, the other teeth can be cut using the same form milling cutter, but in this case it has to be turned to that angle or to that many turns of the indexing plate as have been calculated. Okay. And then the spar gear is ready. It is like the previous as I showed it to you. So, these are the tools that you must have used. Again, the drill chuck for making the center drill, the pilot hole and the subsequent enlarging of the pilot hole, cutting tool. Lathe dog is something new, because when the workpiece is mounted on the centers between the 2 heads, headstock and the tailstock, all right. Then we have to have the this kind of a mechanism, which is the lathe dog, to transmit the rotation from the spindle to the mandrel or to the workpiece. This is the mandrel in this case. This is the dead center which does not rotate, which is mounted at the tailstock. This is also a Morse taper, all right. This is the live center, which is like the dead center, but it is mounted at the normally in the headstock, and this rotates. That is the difference between live center and the dead center. Spanner used, gear cutter, which is used for the cutting the gear, and your gear which you are cutting is here, all right. These are the steps for making the spar gear. I have shown you some slides on the tools which are used, on the measuring tools that are used in the lab, and you will all, as I said, that you will all see them. Now, after that I have told you in details about the technological process of manufacturing and fabricating spar gear as well as a bevel gear. I also told you that in the lab you will see there are conventional machines as well as there are CNC and the NC machines, on which we actually give the hands-on training to the students, to our undergraduate students, irrespective of their disciplines. All the students go through such kind of training, and in the CNC and the NC machines we particularly tell them how to make a part program, so that they could be equipped with making a program for any kind of part that they encounter in the practice. Similarly, I also would like to expose through these discussions all of you to the part programming in the CNC and the NC machines, which you will find rather easy than it is thought of. Now, for the part programming, I will show you some steps for making a part in the on the CNC lathe as well as on the CNC milling machine. These things you will be shown, you will be demonstrated in the laboratory on the machines as well. Now, for making a part, fabricating a part on the CNC machine, first of all we have to make a program manually, and then that program has to be tested in the sense that there are simulators. You will be shown those simulators as well in the lab, but nevertheless I am going to tell you in some details about those simulators and how the simulation is done, so that we could be sure that there is no fault in the program that we have written, we have made for that particular part. I will show you how those simulators work, and then after we get confirmed that there is no error or fault in the part programming, we pass on that program or we put that program on the machine as an input and then run the machine to fabricate the part. So, I will show you in two examples, one in the CNC lathe and another on the CNC milling machine. There is one alternative to that. Now, these days recently they have come up with a program, with a software which actually can produce, there are a lot of different software which can be used to make to generate the NC programming automatically. Now, for that purpose you have to make the part using that software. Then the software itself will take care of getting the coordinates and making the 3D picture along with the tool that we will select, and then it will actually simulate how to make the part. From that simulation, the software then picks up the program which is to be made for fabricating that particular part on the machine. So, therefore, this is an automatically generation of the part programming that I am going to demonstrate you here now through a PowerPoint presentation, and then we will show it to you in the laboratory. Well, then if you look at the PowerPoint presentation, this is the CNC part programming exercises. So, let us take first the example of a turning. Now, here we have the part that we have to generate. This is the part drawing, all right. Now, in this part drawing you can see that this is a part which will have the flat surface, which will have a semicircular profile, which will have a taper surface, and here there is a chamfer. Along with that we will also have a groove here and a thread. Now, all the dimensions are given here. For example, the total diameter of the part should be 24 millimeter, all right. Now, this radius should be 5 millimeter. Here there is a thread which is metric thread of 14 millimeter and 1.5 is the pitch. So, this is how it is written in the drawing, M14 into 1.5. This is the chamfer where you have the 2 millimeter of this distance is 2 millimeter, and normally the chamfer angle is about 45 degree. So, this is to be mentioned, but here it is not. Now, this diameter is 20 millimeter. You understand that here only the half of the part is shown, assuming that this is a symmetric part. So, other half will be symmetrical to this, or the mirror image of this portion. Now, these are the linear dimensions which are given. So, the total length of the part is 43 millimeter. From here it is 37 millimeter is the surface here. Now, you can see that in all these dimensions there is a negative sign here. Going ahead, I should tell you that in case of turning, CNC turning, this is the system of axis. X axis is here and Z axis is here. Out of that, on the top it is the plus for the x, and below the origin it is the minus, this is negative. And along this length, that is the feed direction, along this it is a Z axis, and all the dimensions will have a negative sign if the dimensions are lying to the left of this, and all of them will be having the plus sign when they are lying at the right side of this. All right. Now, this is the origin. So, now you will understand that if we say, if we assume or if we make this point here, this point as the machine origin, okay, which is 0 0. So, all the dimensions which will be lying to the left side of this will have a negative sign along according to this system of axis. So, therefore, these are the dimensions which are made as the negative, but their actually absolute value is 43 millimeter is the total length, 40 millimeter from here to here, and so on. Similarly, the diameters, as you can see that on the top it is x, okay, that is the positive, and below that it is negative. Now, for fabricating this part, of course, you understand that along with this, the groove and the thread, these are also part of the final product. That is, we have to have in the final product a groove like this of 12 millimeter diameter here, and a metric thread of 14 millimeter and the pitch of 1.5. Okay. For this, we select a blank. Okay. This blank we have taken as 70 millimeter into 29 millimeter. Although, if you see that we need only 43 millimeter, so the remaining we have to remove, and in the diameter we have taken the diameter of 29 and we have to get only the 24. Okay. So, this is taken because we have to have some kind of an allowance, okay, so that the hard layers or the stock which is the at the top of this blank, which you might have seen, I have shown it to you earlier, that there is a stock on the at the top of the part blank, and that actually is a oxide of the material which is very hard, and the hardness of that layer is more than the hardness inside the layer. So, therefore, that layer is normally removed, and therefore, along the diameter and along the length some allowance is taken, and for 43 millimeter we have taken 70. Well, if you ask me why not 60, I would say okay, you could have taken 60 as well. That depends on what kind of blank quality that you are having, okay. But it should be more than 43. Okay. So, that allowance that you will be having should be added to the final dimension of the readily available part, readily made part. Thank you for your attention.